All right. Welcome, everyone, to today's webinar, which is part of the Civitas Elliptic webinar series. And this is the second webinar, and we will deal with eBus planning supported with simulation tools. I hope everyone can hear me well. If not, then please use the chat function and let me know that you cannot hear us or you don't see something that you're supposed to see. So let us know if there is something not going so well. My name is Henning Günther. I work for Ruprecht Consult. We are based in Cologne, Germany, and I'm essentially the organizer of the webinar together with Yannick Busse from UITP. So let's see what the program is for today. We have quite a packed program with presenters from research organizations such as RWTH Aachen, Fraunhofer Ivy, and the Free University Brussels. And they will show different aspects of simulation that help in the planning of e-buses. So we have Yannick and myself. We will introduce you, first of all, to the ELIPTIC project. Then Fabian Meissner will talk about e-bus simulation, finding the optimal technical configuration. Then this will be followed by Thoralf Knote, who will talk about conversion of a diesel bus line using hybrid trolleybuses. And he will exemplify this with the use case Eberswalde in Germany. And then last but not least, we will finish with Omar Igazi from the Free University Brussels, who will talk about electrified buses, design considerations, and charging strategy. Just to give you an impression of who is actually talking to you on the other side. I mean, it's always a little awkward if someone is talking to you, but you don't know the actual faces behind this. So just to give you an impression, these are the moderators, Yannick Busse and myself. And we have the three panelists, Fabian Meissner, Professor Igazi, and then Dr. Knote. Yannick Busse is a project manager at the International Association of Public Transport, and he also leads the work in ELIPTIC on the safe integration of e-buses using existing electric public transport infrastructure. Fabian Meissner is a research associate at the Institute of Power Electronics and Electrical Drives at RWTH Aachen. And then Mr. Professor Igazi leads the Power Electronics and Electrical Machines team at the MOBI Research Center. And finally, Mr. Dr. Knote is the head of department at the Fraunhofer Institute for Transportation and Infrastructure Systems. So these are the people that have worked on this webinar, and you will hear later on. Before we actually delve into the content of today's webinar, we need to talk about a few technical aspects for those of you who have never listened or used GoToWebinar before. So it's very important, if you actually want to interact with us and communicate to us, that you dial in. Either you do that through computer audio, so that way you shouldn't have any problems because you can hear us and also talk to us. If you dial in through phone call, then you need to make sure that you've also dialed in with the audio pin, because only the pin access enables you to be unmuted. Otherwise, you cannot speak. Then I said this before. This is a webinar. Of course, there will be quite some big chunks where we are going to talk to you and give a presentation, but this is also supposed to allow for interaction and communication between the two sides. So first of all, we need to say that all of you as attendees of this webinar are muted by default, and only we can unmute you if you raise your hand. So this is the first way of communicating to us, or signaling that you want to communicate to us, is by raising your hand, which you see here. Another way of communicating to us is by putting a question into the question section here, and then either I will individually answer directly to you, or I think that the question is so important that I will afterwards introduce it also to the audience as a whole. But important thing is, by default, you will be muted, so you cannot speak. And this is mostly because we have so many attendees. We have 30 people here in the room, plus the organizers. So in total, we are roughly 35, 40 people. And we would like to avoid any background noise. So by default, you're muted, but again, we can unmute you if you give us a signal. Okay, great. Before we actually delve into the content of today's webinar, we would also like to get a brief impression of who we are actually talking to, because we don't have that much information from you yet. So what I would like to do now is launch a poll. What kind of organization do you represent? And we would like you to quickly partake in this. And I'll wait a little bit more until everyone has given their answer. Okay, we have a 70% voter turnout now. Seems like, yeah, people are still answering. Okay, I'll wait a few seconds more. Okay, and I will share the results with you. So as you can see, we have quite a few people from consultancies. This is roughly 50% of all attendees. And then this is followed by other, which might be, students maybe, but also NGOs. And then this is followed by public transport providers and local administrations. So we have quite a good mix of people here in the room. I'll close the poll again, and then I would hand over to my colleague Yannick Busse from UITP, who will give you an introduction into the ELIPTIC project.
Thank you very much, Henning. Welcome again, everyone, to all the participants. I will talk to you about ELIPTIC and also about the topic that we will be discussing today, which is integration of electric buses into existing public transport, electric public transport. So ELIPTIC is a Horizon 2020 research and innovation project. There are 33 partners in 8 countries. We have 20 use cases. These consist of demonstrations and also feasibility studies. The project has a duration of 3 years and will finish next year at the end of May. And it is being coordinated by the city of Bremen with a budget of nearly 6 million euros. And here you see the concept of the project, basically. So we want to electrify public transport. And the idea is to reduce costs and energy consumption of electric public transport by optimizing the infrastructure and rolling stock. So what this means is we would then use, for example, metro and tram infrastructure to then be able to charge electric buses, electric cars, electric fleets of taxis, of municipal fleets, of electric bicycles. So using this existing infrastructure as the backbone for future electric mobility concepts, and also using this existing infrastructure and also optimizing the existing rolling stock, for example, optimizing the energy use of, for example, metro or tram. So in this way, we would then increase electrification of public transport and also reduce the costs and energy consumption within public transport as well. And then here you see the objectives of the project. So firstly is to evaluate the costs and benefit of these 20 use cases which are being tested at the moment, and also to support the take-up of the business cases and exploitation of the project results across Europe, but also to develop political support for these use cases as well, and for the general electrification of public transport. And we're doing this within 3 thematic pillars. So there's 3 core pillars of the project, 3 areas that we're working on. The first one being the theme of the webinar today, which is e-buses, so integration of electric buses into the existing public transport infrastructure. The second one being energy storage systems, energy efficient public transport systems. So how can we recuperate braking energy from rail, so metro, tram, but also trolley buses, using reversible substations and flywheels, and to increase the energy efficiency within the public transport system. And then the third pillar is then about multi-purpose use of electric public transport infrastructure. So how can we charge, for example, electric cars, electric bicycles, electric taxis using existing infrastructure of trams or metro? Then just to show the project itself, so we have these 20 use cases in cities, 11 cities across Europe. We also have twinning cities, which are twins to the 11 cities in the project, and also a user forum which gives feedback on the results of the project as well, consisting of public transport operators and authorities. And then we have several networks which act as replicators for the results and also disseminate the results to a wider network as well. Here is a summary of some of the outcomes of the project. So this will be to increase the knowledge and awareness of cost-efficient approaches of electric public transport. We'll also evaluate these 20 use cases and also provide a pathway from the use case to the business case. There will be guidelines and policy recommendations. There is the twinning program for these cities. There will be thematic workshops, the next one of which will take place in June, and also moderated webinars, for example, the one which we're having today. So here I give an example of one of the cities taking part in the project. So we have Barcelona. Barcelona is testing opportunity recharging and overnight charging of electric buses on the metro infrastructure. So they have a bus line which has been electrified. You can see on the left-hand side of the screen the picture with the two terminals. And there at the two terminals they have fast charging stations. And also at the depot, they have overnight charging, which you can see in the bottom right picture of the screen. And the fast charging stations have now been installed, and the depot charging is connected to the metro infrastructure, to the metro grid. And they have also done simulations in Barcelona before starting this line. And what they did there was they simulated the viability of this electric line by testing the length of the line, the average consumption by type of bus, whether it be 12 meter or 18 meters, the energy capacity of the batteries of the bus, the state of charge of the batteries, the power of the fast charging station, and also the number of fast recharging stations which they put on the line as well. Then we have Oberhausen, which is another city in ELIPTIC, and they are testing opportunity recharging of electric buses using substations and also tram catenary as well. So they have two electric buses which are in operation since October 2015. And on the top right, the top two pictures, you see the charging using the substation, and on the bottom two pictures you see the charging using the tram catenaries which they have installed. And by doing this, they charge at the turns of the line at the terminals, and it takes up to 10 minutes for this charging, and this has reduced the charging at the depot, which is now no longer required. And this has led also to smaller batteries on the buses itself, which means less weight and also cost savings on the purchase price of the bus as well. And for Oberhausen, they also did simulations of the batteries to simulate the charging cycle and also the range of the vehicle as well. Then, as a final word, I would like to mention we will have also another ELIPTIC event, which will be a workshop on innovative energy storage systems to increase operational efficiency of electric public transport. This will be taking place in June, on the 12th of June, in Rome, which is organized by the Italian Public Transport Association, Astra, which is a partner in the project. And they will be looking at the first results from 3 of the cities with in ELIPTIC, so that's Brussels, Gdynia, and Lanciano. And the information for this event will be put on the ELIPTIC website next week, so it will then be possible also to participate. So having said that, this is the end of the first introductory presentation. If there's any questions at this point, then you are able now to raise your hand. Otherwise, I will be handing over to our first speaker. Okay, so I will then hand over to our first speaker, which is happening now. So Fabian Meissner will talk to us about finding the optimal technical configuration for electric buses using a simulation tool. Fabian, I hand over to you now.
Yeah, thank you, Yannick. And good morning to everyone from my side. Yeah, maybe a short introduction about my background a little bit more. As said, I'm from the Institute for Power Electronics and Electrical Drives of the Aachen University. And there I am a research associate at the chair for electrochemical energy conversion and storage systems of Professor Sauer. So what we basically do, you can see it on the top. We deal with battery aging and so on, every kind of investigation of batteries and especially lithium-ion batteries. So we start from the battery aging, so understanding the basic aging mechanisms on a physical and chemical level, and build battery models from that. Do then battery diagnostics, like battery diagnostics for a battery management system in a car. And we also do battery pack design and look into all kind of applications for energy storages, mainly lithium-ion batteries. So into stationary energy storages, energy system analysis, and also into especially the electromobility, which electric buses are a main part of. So this about the background. Now I want to start with a little motivation. Why are we doing or performing this electric bus simulation? Why is it good, or why should you do this? At first, we can evaluate beforehand a technical feasibility, which means that we want to find out, are there enough charging times? Will there be enough energy inside of the battery to perform the operation? So this is a pretty general look at the first time. But of course, we also then want to evaluate different technological concepts before the implementation and demonstration, like having a look at will the overnight charging work, or should there be opportunity charging because the distance is too long during the whole day. We also have a look then at the different battery technologies that should be used in the different cases. Like for overnight charging, you maybe need a battery with a high energy density and a lot of energy content, but for opportunity charging, you need more a battery that is capable of fast charging. Yeah, that's one thing we look at. And yeah, one advantage of simulation is, of course, that you get fast and valuable results. But of course, it's only simulation and not the reality. So therefore, the input data, of course, has to be as realistic as possible. And the more detailed the input data is, the more valuable the results will be in the end. So this means that we need, for example, good prices of all the components, good data about the reliabilities, and so on. And having this, we can also check the robustness of the system, of the technical configuration against worst case conditions. Worst case means having, for example, a very cold winter day and a lot of auxiliary consumers during the day, and also a high load of people. And how will the system behave in this condition? A next point is that we can, via our simulation, estimate the resulting technical project cost. Technical means that there's more a focus on all the relevant equipment and less on the personnel. I will clarify that later. So you can beforehand estimate what will it maybe cost. And one specialty of our simulation is that we can optimize the technical configuration in order to decrease those costs and to find in the end the best technical solution. Yeah, I will then explain you. So yes, I want to show you everything how it works with an example. So here we want to have a look at the line 73 in Aachen, where we want to have 3 new electric buses driving on. So if you see the picture, you see this bold blue line, it's line 73. This is the main line. So the buses mainly run on this line, going from the main or terminal stops 1, 2, and 3. But there are also other stops like stop 4 to stop 9. And these stops are also driven to by vehicles mainly driving on line 73 during the day. So for example, stop 4 will be a school. So there the vehicles go in the morning and they also go once in the afternoon to pick the school kids back again. So the vehicles do not exclusively drive on their line, so they have also other in daily operation. And in the center you can also see the bus depot. That's where the buses are then overnight located. So this is our basis. What are we doing now? From these route profiles, or from these vehicle schedules and then this information, we create route profiles in detail. So for every route, for every trip, we create a detailed route which takes into account traffic lights, speed zones, of course the height profile, which is pretty important for the energy consumption, and also curves. So we really model all the routes in detail. And if we have all these detailed route profiles, we then want to calculate the power profile so that we know at each time point what is the required power for the vehicle. And we do this via a vehicle and driver model. So we have take into account also the traction resistance, of course, but also the regenerative braking and different efficiencies for the powertrain, for the engine, power electronics, battery, but of course also the additional effect of auxiliary consumers, mainly caused by heating or air conditioning. So, and you can see it on the bottom right picture, we then get a profile of the power. This is the black one, derived from the profile of the vehicle speed, which is the blue one, so that we really know for each time step what is the power required or the power in the vehicle. So what is now our investigation, or what is the question? What do we find out? We want to find the configuration which has in the end the lowest total cost of ownership, the technical configuration. And what do we have a look at basically then? At first on the left table you see we start with the battery capacity. So we want to find out what is the best battery capacity in terms of energy content for the 3 buses. So mainly how big should the battery be? And the second question is, where do we put the charging stations and where or how big will they be, or what will be their rated power, so that the operation will be safe through every day and also in worst case conditions. So here you can see it on the right, we have several yellow sparks. These mark locations where there are possible charging stations installed. And now we want to find out where it will be the best. And some other parameters are for this investigation now that we have a time frame we look at of 12 years, and that we can take an interest rate of 4% for the calculation of the net present value within the calculation. So What is now the system model or the whole system that we look at? We start on the left. So we start with the power supply, with the grid connection. Are there any building costs, subsidies maybe? What is the connection charge? The connection charge dependent on the power. And what is the network charge? Then there's also the question if a new transformer has to be installed and a rectifier. What are the overall constructional measures for this? Are there any big civil works that have to be done? Yeah, that's mainly getting into the cost there. Then, of course, we have a look at the charging station. Is there a DC-DC charging station, or is it an onboard charger in the bus? What is the coupling assembly? Is it via a plug, or will there be a kind of a pantograph? And yeah, of course, for these components, we have to know detailed prices, and also we have to know or somehow evaluate what is the reliability and the lifetime of these components. And then, of course, we look in detail at the vehicle, so at the electrical machine. Yeah, mainly what is the regenerative braking potential and the overall efficiency. Then what are the auxiliary consumers? Is there an electric heating, or is there maybe a diesel fueled heating and other consumers? And of course, what is our main interest is the battery in the vehicle, and also to estimate or have a look at how is the battery behaving under the operation conditions. Are there too high currents for the battery? Or how is the battery aging, behaving? Will the battery live not that long because it's cycled too much, or does it have a good lifetime in this operation? So really have a deep focus on the battery, and also different types of batteries and technologies, like having fast charging battery with lithium titanate oxide, or having a more slow charge iron phosphate batteries. So that's one thing we have a look at. So how is now the overall total cost of ownership composed in our simulation? I start on the bottom. So one big part is, of course, for the vehicles, for their asset, inclusively the electric machine, or we also always compare to diesel buses, the diesel engine. And yeah, if installed for the electric buses, the onboard coupling device, so maybe the pantograph, if you have pantograph charging, but not included in the vehicle part is the battery system, because that's regarded separately, because we assume that the vehicle will live longer than most of the battery systems, probably. Then one big point is the maintenance for the vehicles. So mainly the maintenance cost per kilometer or per year, and also insurance. Then the battery system, on cell level, for the packaging and for all the system components, and also regarding the lifetime, maybe for a second battery system that has to be installed in the bus. And then the charging infrastructure, so the main chargers, their main price, and also the maintenance for it. The coupling device, the stationary coupling device, which would be maybe such a tower for pantograph charging. Then, of course, the grid connection cost and constructional measures. These are only one-time expenses for building up the charging infrastructure. And then on top, the energy cost for diesel, if we have a look at a diesel vehicle in comparison, of course, per liter. But for the electric buses, of course, the electricity, what is the price we have to pay for the kilowatt hour, including subsidies and taxes, and also the grid utilization, if there is one, per kilowatt and per kilowatt hour. So how is our simulative approach now? We start on the top left, having our database. Our database is mainly that we have the schedules, that we have the vehicle schedules. So we know at each time point during the whole day, during the whole year, where is our vehicle, or where will our vehicle be. And yeah, from that, then we also need, of course, the parameters, all the cost parameters, the lifetime, estimated lifetime, and so on for all the technical components. And having this, we can then define a first scenario, which means that we choose a battery capacity for the 3 buses or for each bus individually, and we choose some locations and power of charging stations. And for this scenario or technical configuration, we then calculate with our simulation the total cost of ownership. So we play it through for 12 years and look how it's behaving. Is it working? If it's not working, so if the state of charge maybe goes below a certain threshold, or if the total weight is somehow not possible to obtain, then there will be penalties which increase the TCO and make the whole scenario not so attractive. So, and to evaluate this TCO, then this is also done by a fitness function who has a look at it and who then feeds an possible algorithm, an optimization algorithm to adjust the configuration. So the next step would be then that this algorithm chooses new input parameters, so it chooses a new battery capacity and new locations and power of charging stations, and then again the total cost of ownership are calculated, evaluated, and so on. So this is all done within a loop until in the end, on the bottom, you get your optimized configuration, or one optimized configuration in the end, which has then the lowest total cost of ownership. And how good this result will be is, of course, very dependent on how detailed or how clear you set your input parameters. So maybe for this example now, if we have a look at the total cost of ownership calculation for our Aachen scenario, we have here a first scenario where you can see there's a lot of charging stations and charging power installed. So at nearly each stop and also in the depot, and the energy content of the battery is a little bit above 100 kilowatt hours. So we see it's pretty good for the battery and for the operation, which will be pretty safe because the state of charge of the batteries, you can see it on a bottom picture, will be always within a small range of only 20% from 10 to the evening. So yeah, this will be pretty safe for operation and good for the battery, but yeah, we will have, of course, because we have to install so much charging infrastructure here, high remaining total cost of ownership. Here, in this case, a little bit above 3 million euro. So this will be probably not the best solution and not that attractive. So now we let our optimization loop run, and different scenarios are now calculated again and again. The charging stations are changed, the battery content is changed, until in the end, then we have a configuration that is working, that is good, and that is cost effective. And this would be in this case here after 1,600 iterations. So this would be then our result. You can see it here. We have now 3 charging stations, 3 charging points. One at stop 1 with a little bit above 100 kilowatt rated power. One at stop 8 with nearly 300 or between 250 and 300 kilowatt rated power. And an overnight charging with a lower power of 100 kilowatt maximum in the depot overnight. And the energy content of our battery would then be 100, a little bit above 100 kilowatt hours. And you can see it in the picture that for all the vehicles, the state of charge range, which has been defined between 20 and 90%, will be obtained during the whole operation. So the operation will work. The battery aging will be in a frame that is acceptable. So overall, we get here the best technical configuration for this special purpose. So, and we can also here maybe have a look at all the loads for the vehicles. It's just here somehow shown for the vehicle 3. So we have in blue the state of charge of the battery. The red line is the charging power in kilowatt that is provided at each stop where there's a charging station to the vehicle. And you can see the vehicle starts in the morning, with a state of charge of 80% in this case from the depot, drives then until it's somewhere between 8 and 9 charged for the first time with a very high power, to then be charged a second time between 9 and 12, and goes then through the whole day. The state of charge is always not in a critical area, and it comes back into the depot somewhat after 18 o'clock and is then recharged again to 80% in this case, and is there overnight. So we can have a detailed look at all the load profiles for all the vehicles, all the days and everything, and also have a look if it's also working like this under worst case conditions. So, and this would then be our final result here again. So we now have our battery capacity of 125 kilowatt hours for all the 3 buses, so in each bus. We have, where the yellow sparks are now, 3 charging spots at stop 1, stop 8, and in the bus depot. At stop 1 with 125 kilowatts. At stop 8, this is the stop where they drive in the morning, 270 kilowatts, and overnight charger in the bus depot of maximal power of 100 kilowatt. And the cash value of the resulting total cost for this scenario, for this configuration, would then be 2.38 million euro. So that's it from my side.
Okay, thank you very much, Fabian. I would like to open for questions. If you would like to raise a question, then please raise your hand and we will unmute your microphone so you'll be able to ask a question. I see we have already one question from Annegret, so I will unmute and then you can ask your question. Annegret, over to you.
Yeah, hello everybody. My name is Annegret Frenze from Signon GmbH in Dresden, and I've got a question concerning the actual traffic on the bus routes. So, Fabian, how do you take into account the actual traffic on the bus routes? I think they will drive on the same routes like the cars and so on. Mm-hmm. This traffic will obviously affect the driving modes and though also the energy consumption. So, how do you take this into account in your simulation?
Mm-hmm. We take it into account by having, of course, we take the vehicle schedules as they are. So maybe for an example, we have a look at also in Barcelona within the ELIPTIC project, where there are also during the day, there's more traffic than maybe having in the late evening or so. So we take it into account by saying, okay, now we have a longer time for the same distance. So that's mainly how the traffic is regarded. And of course, we take into account that there is, due to traffic, different maybe charging times. So let's say, okay, there was high traffic and now we have 3 minutes less for charging. So we have always kind of a buffer that you can define for that.
Mm-hmm. Yeah. Okay, but the due to high traffic, you have more often situations where the bus stops and runs again. So they have acceleration, deceleration, which mm-hmm. I think also has an effect on the energy consumption. But you do, as I understand it right, you do not take this into account at the moment in your simulation.
No, it's taken into account, because if we have the same route but have to go for the same route now, have more time, then of course we create more stops. So we create more stopping and accelerating events. So that's exactly what is done then.
You do not just put down the speed of the bus to get the longer drive. You really create more stops.
Yes.
And you do it just like symmetric model, or you put stops by accident, or what do you use to create
basically
these?
done via an algorithm just to pull up the time, and yeah, it's not detailed handbook, I would say.
Okay. Thank you.
Thank you very much. Okay, thank you, Fabian. Then I would like to hand over to our next speaker, which is Dr. Thoralf Knote, who will be talking to us about converting a diesel bus line into a trolley hybrid line in Eberswalde. Thoralf, you have the microphone, and over to you now.
Okay, thank you, Yannick. Good morning, everybody. My name is Thoralf Knote, and I'm head of department for vehicle and transport system engineering at Fraunhofer IVI in Dresden. And this presentation is done in cooperation with Mr. Vrook, who is the CEO of Barnimer Busgesellschaft, the local transport operator of Eberswalde. Just for the one of you who do not know where Eberswalde is situated, it's approximately 50 to 60 kilometers northeast of Berlin. It is a pretty small city with just 39,000 inhabitants, which is normally too small for the operation of trolley buses. But I will show you later on that Eberswalde is, for good reason, 1 out of 3 German trolleybus towns, because it has a very elongated urban structure. And the ELIPTIC use case was a feasibility study on hybrid trolleybuses in order to convert an existing diesel bus line into a trolleybus line. Just as introduction, I would like to show you the existing trolleybus network, which also somehow resembles the urban structure of Eberswalde, which is a stretch of a settlement. And at the moment, we have 2 trolleybus lines, which is 861 from North End to the Big Star or Großer Stern, and 862 from Ostend also to the eastern part of the city. The use case we are talking about is the conversion of diesel bus line 910, which connects the neighboring Finofort with Eberswalde. It has it runs partly in parallel to the trolleybus lines, which gave the idea, or which prompted the idea to operate this diesel bus line with hybrid trolleybuses which are equipped with a storage, energy storage. The length of the diesel bus line 910 is approximately 14.7 kilometers, which depends on the terminal stop in Finofort. And as mentioned before, it connects Finofort with Eberswalde. The idea about the combination of line 910 with the existing trolleybus catenary network was to use the existing catenary network and do as little extension as possible. And of course, this requires the utilization of trolleybuses with an energy storage instead of an autonomous power unit. For that, Eberswalde bought I think 4 or 5 years ago 12 new trolleybuses from the manufacturer Solaris, and one of those 12 buses is already equipped with a battery, which was supposed to be the basis for this hybrid trolleybus operation of line 910. And the question or the intention is to retrofit additional buses in order to fully operate line 910 using those hybrid trolleybuses, but this was subject to the feasibility study, and as I will show you later on, it was good to carry out the feasibility study beforehand, because the buses, as they are configured right now, will not be able to be operated on for this purpose. Let's have a look at the buses. Closer look at the buses. They are conventional, more or less conventional or normal hybrid, normal trolley buses. In this case, equipped with a battery. We have an energy content of roughly, or something about 74 kilowatt hours, of which 42.2 kilowatt hours are usable. What is important, and therefore I underlined this figure, we have only a charging power of 38 kilowatts and a discharging power of 140 kilowatts. The discharging power is okay, but the charging power limits the possibilities to operate the buses on line 910, as I will show you later on. Additionally, we have a braking energy storage, which is in this case a supercapacitor with an energy content of 0.57 kilowatt hours, which also supports the acceleration of the vehicles while not driving under the catenaries. We carried out this feasibility study using our in-house vehicle simulation tool iVision, which is, and this is a difference to the approach from RWTH Aachen, which is based on measured speed distance patterns or speed time patterns. iVision roughly consists of the vehicle and infrastructure data, which has to be put into the simulation tool. We always carry out measurements. We never use artificial speed profiles, because from our point of view, or based on our experiences, it would be practically suicidal to use artificial speed profiles. Then inside the simulation tool, the vehicle configuration and the infrastructure data are converted into text files, and the very simulation and optimization is done using Ivy Drive, which is in our opinion, pretty sophisticated vehicle simulation tool with which we can simulate a lot of different vehicle configurations. What were the core questions of this feasibility study? The first one is a battery big enough to cover the catenary-free section to and from Phenofort? And the second core question is there enough time under the catenaries to recharge the battery for another journey to Phenofort? And then there are three secondary questions. How long must the additional catenary be? And the second one is there a charging station at the terminal stop in Phenofort necessary? And finally, are additional trolleybuses necessary? This question has been pre-answered or pre-decided by the local transport operator, because he decided that the schedules of the buses running on line 910 will not be mixed with the schedules of the existing trolleybus lines. In the first step, we carried out field measurements for which we equipped one of the running buses with measurement equipment. We measured the speed distance patterns and the speed time patterns, and of course we measured, or we counted the passenger demand, because this is a has a big influence on the results. Afterwards, we configured the vehicle model and the catenary network using the existing catenary network, and of course the data we got on the vehicles, and then we carried out the vehicle simulations using the schedules provided by BBG. Let's have a look at the different layouts for the catenaries. First, we looked at the existing catenary with just one extension to the west. Then the second extension to the west, and then we also considered the additional extensions to the east. What is very important in such simulations is the determination of the charging power. We decided to be a bit conservative and just allowed energy or electric power taken from the catenary of 240 kilowatts while driving. This could be higher, but a higher charging power does not necessarily result in another result, because the recharging of the battery was limited by the converter, the vehicle internal converter of the batteries. And during stops, we allowed power and electric power taken from the catenary of just 90 kilowatts, which is okay. Some say it is too much, some say it's too low, but in our opinion, it's a good value. Then we considered four different versions or two different versions for the HVAC system. The first one is with a heat pump or fully electric heater, and we also considered the use of delta Kelvin air conditioning units inside the buses. The objective, and this has been made clear by the BBG, was to have a fully electric operation. The diesel heater therefore only served as a kind of comparison regarding what is the minimum energy electric energy requirements for such an operation. And finally, we had to look at the ambient conditions in three scenarios, and finally the worst case scenarios were scenario S1 and S3, which represented first an overcast and very cold day, and in the second scenario a very sunny and hot day in the summer. However, the worst scenario, or the determining scenario, was the winter scenario, which we considered in two versions. The first one was to have real measured data from the history, and this was a day between -17 and -24 centigrades, which is rather unusual. Therefore, we decided to have a second scenario with a minimum temperature of -15 degrees Celsius. And then we used three schedules provided by BBG with a daily mileage between 260 and 350 kilometers, and we considered two scenarios. One is the two scenarios regarding the passenger demand. The first one is a constant passenger demand of 25 passengers, which represents roughly the real passenger demand over the day as an average. And the second one was also to have to consider peaks during the rush hours in the morning and in the afternoon. Yes, a very important point regarding this feasibility study was the heat losses, which is widely influenced by the duration of the open doors. And we considered heat emissions of every passenger between 50 and 100 watts, depending on the assumed clothing they are wearing. Let's have a look at the results. First, we have the energy consumption for the different use cases or for the different scenarios. Here you can see the specific energy consumption in kilowatt hours per kilometer, or the total energy consumption. And not quite surprisingly, the winter use case or winter scenario leads to a very high specific energy consumption of approximately 3.5 kilowatt hours per kilometer, out of which more than half is caused by the electric heating system. This also shows the necessity for further research and development regarding efficient electric heating systems. And then we have a look at the state of charge of the batteries, because this state of charge determines the question whether the feasibility of this operation is given. And the first one, what you see here, is a figure showing the power demand of the battery and sorry, it's a state of charge of the supercapacitors, which is a black line, and the state of charge of the batteries. And this is for scenario S2, which is mild weather conditions, 15 degrees Celsius. So we have almost no heating, and we have we definitely have no energy consumption by the air conditioning. And as you can see here, the purple line representing the state of charge of the battery, we are always able to keep the state of charge somewhere between 65 and 85%. And this state of charge can be reached throughout the day. Whereas if we have a look at the scenario S1, which represents the cold weather conditions, here you see that we have a very deep drop on the state of charge. After the first journey to Finofort, we already have here's Finofort, and then we go back to the catenary. We have a drop down to 40% state of charge, and due to the low charging power of the catenary of the battery converter, we are not able to recharge the battery to 80% or 85% until we reach the end of the catenaries in the direction of Finofort again, and this results into a stop of simulation after approximately 2.8 hours when we reached a state of charge which is too low for further operation. And therefore, so I come already to the conclusions. The answer, and which gives the answers to the questions: is the battery big enough to cover the catenary free section to and from Finofort? Yes, it is, assuming a higher charging power for the batteries. Is there enough time under the catenaries to recharge the battery? No, it's not, because the charging power of just 38 kilowatts is too low. And how long must the additional catenary be? The answer is pretty simple. It must be longer than possible. and therefore with this vehicle configuration it is not possible to operate the buses. A solution would be a charging station at the terminal stop in Finofort. Yes, it would help, but the very high investment costs are an opposite to the rewards, and therefore BBG decided not to invest into such a charging station. And the solution would be a battery with a higher charging power, not necessarily with a higher energy content. This would mean that the supercapacitor storage must be eliminated, and the weight reserve we reach through that or by that would help us to install a battery with a higher charging power and with the same energy content. And we would use supercapacitor converters to recharge the battery because they can provide a much higher charging power. And therefore, we currently carry out additional analysis for BBG in order to determine the usable energy content and the charging power of the battery, which will be necessary for the operation as intended. And that leaves me with the last slide, and thank you for your attention.
Thank you very much, Thoralf. So now I would like to open up to the participants if there's any questions. If there's questions, please raise your hand and then we can open up your microphone. At the moment, we don't have any questions, so actually I have a question for you, Thoralf. Maybe you could tell us a bit how reliable simulations like these are in your experience.
Simulations are always a kind of modeling of the natural events of nature, and the reliability on simulations always depend on the input data, of course. There's a simple saying, garbage in, garbage out, which you have to avoid. From our point of view, it is extremely important to use measured and real drive cycles for two reasons. The first one has been raised in the past. Before I started my presentation, it is from our point of view, we think it is necessary to consider the real driving, or to model the real driving behavior. And the second point is the schedules are, well, politely speaking, a kind of wish on how to operate the buses, but you have to consider delays, and for this it is necessary to carry out measurements. But if you stick to those simple rules, be as close to the practical operation as possible, and have a good simulation tool, then the results are pretty reliable.
Okay, thank you. We have a question from a participant. I will from Slobodan. I will unmute your microphone now, and you can raise your question. Over to you, Slobodan.
Thank you very much. Hello from Belgrade, from a public transport company. Here with me, my colleagues Pavle Krstic from Trolleybus Depot, and Pavle and me, member of UITP. I'm member of bus committee, Pavle from Trolleybuses committee. I want to know some information about consumption during winter period, but exchange some experience. As you know, in Belgrade, last autumn we started with operation with 5 electric buses on one central line in Belgrade, and during the autumn period, when not use air condition, we have a consumption about 1 kWh per kilometer.
Is it a articulated bus?
No, standard buses.
Okay.
And what is interesting during winter period, this winter in Belgrade very, very cold, and our experience that during extremely cold day in Belgrade, about minus 10 degrees and minus 15, we have a consumption higher to 2 kilowatt-hour per kilometer. Double. But all system for heating with electric heating with Sferos system. And after then the colleagues from Sferos visited Belgrade, and now they worked about optimization system of heating. And they believe that forecast that about 40% will be less consumption on the next winter, and I believe that is correct. And I see that, for example, from double trolleybuses, 3.5 kilowatt-hour per kilometer is consumption during extremely winter operation, and it is very, very interesting. And for me, one question.
But if I can answer the first underlying question, if you I assume that you had a energy consumption of approximately 2.0 kilowatt hours per kilometer with your standard bus during the cold winter, right? Is that correct?
Yes.
So if you multiply it by 1.5, then you are already with 3 kilowatt hours per kilometer, representing an articulated bus. And then we have to compare the inside temperature requirements, and we use the VDV inside temperatures, which says a minimum of 15 degrees Celsius must be ensured in the passenger compartment.
Yes, I agree. And the second question about simulation of consumption buses during operation in relation about configuration of route declined or no, or passengers flow and exploitation operation speed. Do you use sort driving cycles for calculation of consumption?
Never, because we know from sort simulations that sort drive cycles hardly represent real operational conditions. So
for example, sort one, for city cycles.
We never carry out, or we only if the customer asks us to do so, but we always suggest to carry out measurements beforehand and use real drive cycles for simulations.
Yes. Okay, I understand. Yes, sort is theoretical cycles. Okay, thank you very much.
More importantly, sort drive cycles, for instance, do not consider the opening and closing of doors properly, which is very important for worst-case simulations in wintertime, because the heat losses during opening and closing of doors is very high.
Yes, I agree. Okay, today I believe that your presentation will be published on your site, ELIPTIC, or we received to our email.
I think that UITP will publish it. Otherwise, you see my email address, and please feel free to contact me directly.
Okay.
All presentations will be made public on the ELIPTIC website still today. So you can check out the ELIPTIC website afterwards and you'll find everything. But Yannick will say this later on again.
Okay, thank you.
Okay, thank you very much, Slobodan, and thank you, Toralf. Then I would like to move on to our next speaker, which is Professor Omar Hegazi. Omar will talk to us about charging strategies for electric buses in Brussels.
So,
very good. Okay, Omar, over to you now. Thank you.
Now you hear me well, I guess. Good morning, everybody. I'm Omar Hegazi. I'm the team leader of Power Electronics and Electric Machine in BUB MOBI team. So today I will share with you our feasibility study in Brussels for electrification of public transport. My presentation will go over design consideration and charging strategy. I will come back to what is the background of that. So as you can see in my screen, background is mean electrification of diesel buses. Why? So we can answer that to improve our air quality and to reduce the noise of buses in city, and also we can get more energy efficient technology. As you can see in Brussels, also there are some standard buses that are running on road now. Is the standard bus 12 meter and articulated buses is 18 meter. So my presentation outline is use case of Brussels, definition and specification, and then I will show with you roughly the modeling methodology and bus architecture and the scenario of charging and battery sizing for electrification or electrified buses, and I will end up by summary. So I will start with use cases definition. So in order to define the use cases, we need to focus on design consideration. So first, we need to know what is the road characteristics. So we need to see the altitude of the road, and we define the road that will be electrified, the buses on it, and battery chemistry, which battery chemistry that could be used, battery aging, charging scenario, overnight, opportunity charge, and so on, charging power and charging time, and what is the impact of the auxiliary loads, include the air condition and so on. Bus schedule, there is an effect or impact on the bus schedule, there is a delay or not, and then bus autonomy and capacity. So I will go for bus lines in Brussels. So in Brussels, MEBB or Steve, they defined the way of the line, how we are going to charge them, and the required autonomy for these buses. So in this case study, we have defined 3 lines, different load capacity and so on. So bus line 1 is 86, and the bus operator defined that we are going to use overnight charger, and we need to satisfy the need of the operation is 12 autonomy range, is mean 12-hour operation. And another line is heavy duty, is 48 line, and this articulated bus is 80 meter, and there we define where we can put opportunity charger. And then we have the last 3 line, the third line is line 17, is neighborhood buses or line route, and this is also a standard buses, and we are going to use overnight charger with 12-hour operation. So this is the 3 lines. So as you can see, it's different number of stops, different way of road as well. And then you see also the focus of MEBB in Brussels, that is this a possibility to integrate the charger to the existing network of metro or tram. So there is a need to also investigate the feasibility of using the DC network, and now we can get in the TCO. So this is a line and how we integrate it or interact with other transport means. So here I will start with the modelation or modeling approach that we use and bus architecture. So as you can see, there are two different ways to model the bus. So we have backward approach and forward approach. As you can see here, the positive power flow comes from the battery to the wheel, and the calculation is coming from the drive cycle to size the battery. And another way is also positive from battery to wheel, but the direction of the calculation is different. So we come out with we start with the battery and then we size all the components. So this is the focus of our feasibility study, that we use our simulation tool on backward calculation, and on which E-bus architectures, that we have two main architectures of high voltage battery. So the voltage vary from 600 to 700 is the DC link, 750, and you have the battery and the auxiliary and the inverter and the possibility of charging and so on. And then we have another one, instead of use high voltage battery, use low voltage battery. And in this case, we have to integrate another device called DC converter to boost the DC voltage to 700 or 750. And our focus to have high voltage. So what is the input that we get from MVVB? So MVVB give us more detail about the lines, and did a lot of measurements on road for different lines, different day schedule, so weekend and also working day, and also different time domain. And VUB also select some battery style or battery technology that mostly used in electrification. Now we use LTO, LEP, and NMC with different rate, as you can see in my screen now. What is the energy per kilometer, what is the power per kilometer, and what is the expected weight. And all of this battery has been, battery model has been validated, and accurately aging estimation is included. So I will go again for lines. So I will start with line 86. So it's diesel bus. So the idea of our bus operator, that is how we are going to electrify these buses. So we receive the measurement for real drive cycle. So it means that I will come back again for the feedback from our participants, that we didn't use sort, because sort is not realistic for this application now. And we use real measurement. As you can see, this one line, and we have the drive cycle on the vehicle cycle, vehicle speed, and then we calculate, we measure also the fuel consumption for the diesel. And as you can see here, the diesel fuel consumption is around 59 liters per 100 kilometer, and the distance is around 13.6. So what we have to do, we use our simulation tool, and we do the same drive cycle, back-forth cycle, and the idea is to show you what is the power of the wheel that we requested from the electric buses, and the power requested from the battery. As you can see here, that this figure shows that the trend between the wheel power and the battery power, and we assume the auxiliary is 3 kilowatt, and I will come back now later on for the auxiliary consumption, how this will influence the consumption of the energy. And in this case, we use LV 45 ampere hour and 700 volt. As you can see here, also we make a lot of study on the state of health, the range. We go really for minimum state of health and see what is the impact on the size of the battery, and then also we go for higher state of health, state of charge battery, and then we go for how we are going to size this battery and give the right sizing of the battery within optimization techniques. So as you can see here, based on this line and based on the minimum state charge and operation of 12 hour, that we got battery size LP is around 175 kilowatt, and the distance that the traveling distance is around 103. So it means that is around, the consumption per kilometer is around 1.7 kilowatt hour per kilometer. And you can see here the trend of the energy consumption. So we have the y-axis is energy consumption, and the timing of the operation. So this is the trend of LFV. So, and we did also some trade-off between different chemistries. So if you are going to use LTO with 6 ampere hour, and NMC of 20 ampere hour, and LEP with 40 ampere hour, this is the trend. What is the required energy to supply this bus in this road? So the operation is 12 hour, and the need to charge this battery at depot is around 40 kilowatt. and the charging time will be around 4.25 hours. That we have this analysis for different batteries, technology, and we come out what is the needed charging power at depot. And here I get also a small investigation on the auxiliary impact of the consumption, of the total consumption. If I assume that the average power of the auxiliary is 3, is around 21% of the total consumption, total energy of the bus. And if you assume the average power of the auxiliary is around 7 kilowatt, we come out with around 40% of the total consumption of the bus. Maybe there is worst case in winter, maybe it could be 60% of the total consumption or total energy that required from the battery. It means that the auxiliary get more energy than the traction. So this could be happening also in some city and some weather condition. So, and again, this is for line 86, and we come out with, we move to line 48, is articulated bus, is 18 meter, and we need to see how we are going to make the sizing in the battery with charging or opportunity charger. So as you can see here, if you go for back force based on the measurement that we get from MEVB, the bus operator, we come out with 50.5 kilowatt hour required for traveling distance of 70 kilometers. Do you mean that's around almost 3 kilowatt hour per kilometer if you are going to use LTO battery type with 60 ampere hour and 600 volt. As you can see here, this is the result of on-road charger at terminals. So it means that at the starting point of the buses and at the end of the line. So as you can see here, this is the charging variation of the battery on the screen now. Is varying from 90 or up to 18 percent. So based on this analysis, and we could optimizing the power need and the timing that you could have available on the stop. So we come out with 200 kilowatt for 7-minute charging on road. So this will be enough that we charge the battery of 28 kilowatt hour at both terminal. And we did also the same analysis for articulated bus for the auxiliary. As you can see here, also the trend of varying the auxiliary power. So if we start with 3 kilowatt hour, and average consumption is around 9%. If you go for 7 kilowatt hour, average consumption for the auxiliary is around 22%. Of course, if you have another weather condition, that could be also included as a constraint in optimization. So this regarding to articulated bus. And then we go for the third line, is line 17, is a standard bus with 12 meter, and we did the same. We received the measurement and we apply this measurement or add this measurement as an input to our simulation. And for back force driving cycle, as you can see here in my screen, the result of required power from battery and the required power from wheel. And then in this simulation, in this case of the simulation, we assume the auxiliary power is 3 kilowatt is assumption. And in this case, we use another battery type is NMC 20 ampere hour for 700 volt. And I will share with you the result. What is the result of this line? If you are going to electrify this line, what is the size of the battery? So we get from our simulation is around 265 kilowatt hour for traveling distance is 211 kilometer, and it's 12 hour operation, bus operation, and overnight charging of 60 kilowatts. And the charging time required to charge this huge battery is 4.5 hours needed. And as you can see, if you calculate from the traveling distance and the required energy, we come out with 1.3 kilowatt hour per kilometer. Of course, if you account or if you include the worst cases, will be varying up to 1.6 kilowatt hour per kilometer. As you can see in my screen, this is a variation of the voltage of the battery and the expected discharge of the battery. So this is the result of this battery size for this line. And I will come out with a summary due to the time. So I will come out with a summary. As you can see, for different lines, we have line 86 and line 48 and line 17. So the energy required for LEV type for the first one is 185, and override charger with 40 kilowatt, and the required time charging is 4 to 25 hours. And for articulated buses, the required energy is 28 kilowatt hour, and LTO battery type, and the need of opportunity charger is 200 kilowatt, and we could charge the battery with 7 minutes. And line 17 is 26.5, the 265 kilowatt hour, and the charging need for that is 60 kilowatt, and the time is required is 4 to 5 hours. So based on our analysis, we found that NMC is not recommended for opportunity charger due to its limits for charging rate. And it's recommended to charge NMC around 1C. So it's not recommended to use it on road charging possibility. Auxiliary road has a lot or high significant impact on the bus consumption. And we also conclude that the emissions, what the expected emissions or CO2 equivalent emission, we did also analysis on tank to wheel and wheel to tank, and we come out with this result, as you can see in my screen, that of course electric bus could have an improvement on the environmental issues like CO2. So I would conclude my presentation. I hope I didn't exceed the time, and I'm willing to hear your comments. Thank you for listening to me.
Okay, thank you, Omar. Again, if there's any questions, then please feel free to raise your hand or put this in the question box. You can do this. In the meantime, I will already ask a question to Omar. Omar, do you already see any possibilities to integrate this operation into the existing metro or tram network of Brussels?
Yeah, this is really a good opportunity, because I will go back again to my first slide for the lines, because based on the request of MEVB or bus operator in city, I will back again for the line that you see what I mean by integration to the lines or metro. I hope I can reach now in a second. I know this is slow. I'm sorry. Yes, as you can see my screen. So we focus on maybe 48 bus line we have here on my screen, that we have integration with the tram, as you can see in my screen now, indoors. And we have also integration to the tram at the end or before the end. So it means that if MEB would like to include the charging, we could be included in the second stop, and they should locate another new one at the end. This for line 48. But if you go for 86, we have a lot of opportunity, because the end is metro and the tram, so we can make use of this to be used as the integration for future line. And also, MEB are willing to change the road to make more interaction with the new lines are planned to be integrated in Brussels. So this is the idea that how we are going to gain from integration of a charging of high power charging to the DC network. The DC network is this added value, because you really need to have again the electrification from the grid to add AC DC and also transformer, and then you have again DC converter to control the power flow to the battery. So this will have the potential that you improve the TCO of the system.
Okay. Then we also received a question in the chat box, in the questions box, about the information. So your research group MOBI as a source of battery data. Is it possible to have a link to more information about this, maybe to your research group or to possible data? Could you maybe include this in your slides in the presentation that we will make available then?
Well, for the raw data, it could be not easy to do it because it has been done for another projects. So what we did is that we have a huge data for the library of battery, include the aging with different current C rate, and we use this possibility that at the library that we could use our optimization to select which library, which battery that could be used. But I would. Of course, I would share it, but due to the confidentiality of the other project, that I could not share the data for the battery itself. But I could give more detail about which more type of battery that we have in our library.
Okay, very well. All right, then I would like to thank Omar for the presentation. And then, okay, then I would also like to thank then everyone for participating today. And you will be able to find material from the presentations on the ELIPTIC website and also on the ELIPTIC training platform. You'll also be able to, you can follow the project on Twitter on ELIPTIC. And there's also a LinkedIn group where you can join as well to get more information about the project as well. So there will also be a follow-up survey for all the participants, so you should be receiving this tomorrow. So please fill this in so we can have feedback about your experience of the webinar. Then I'd like to thank all of our speakers, Fabian Meissner, Dr. Thoralf Knote, and Professor Omar Hegazi for their presentations today, and also Henning Günther for the organization of the webinar. And we hope to see you soon at the next ELIPTIC event. The workshop in June in Rome would be a great opportunity there. So thank you very much all for participating, and goodbye. Thanks.
Thank you, everyone. Bye-bye.
Thank you. Bye.
Yep. Bye.